Welcome to our talk on accelerating AI workloads. I'm Sean Kelly, a principal architect that covers AI at VMware, and I'm joined by Justin. Go ahead, Justin.
Justin Murray, product marketing engineer at VCF in Palo Alto as well. And I'll be back later. I'm going to hand the floor to Sean.
Yeah, we decided just to divide it up into two pieces, and I'll hand it over to Justin about halfway through. Standard disclaimer. You're going to see this in every talk, basically just saying that anything that we have that's forward-looking, no promises that it's going to wind up in the software. Everything that Justin and I are talking about today, though, is already in the software, so it doesn't really apply too much to us. Obviously, GPUs is a big topic today, but before we dive into the weeds on that, I want to talk a little bit about some of the recent services that we've brought out with version 9. Model Store is, just as it sounds like, this is a repo that you would deploy on premises. It's actually open source Harbor, been running with containers for a while, and we've extended it to leverage models. Next, we have Model Runtime and API Gateway. This is just an easy button for you all, your teams, to be able to deploy models as a service. After that, data indexing and retrieval. Again, another easy button for you to leverage your internal data, whether it's in a SharePoint, Confluence, Google Drive, the usual suspects. And then finally, Agent Builder, exactly what it sounds like, building agents. This topic is going to be covered in multiple sessions, including, I think, some of the general sessions. So I'm not going to dive into it too much, except for the Model Runtime and API Gateway. This applies because we're talking about GPUs. And at the end of the day, when we're deploying a model, under the covers, it's going to be leveraging some sort of GPU most of the time, not always. And so here's what the software looks like. As I mentioned, it's an easy button where you can really quickly go in and identify the resources that you need. And I've actually skipped multiple steps in here just to keep this moving along. We have a lot to talk about in a short period of time, but in the beginning, you identify the name, describe it. Next set of forms, it gets into some of the details about the model and the actual engine you want to be leveraging to run it. And then after that, we get into the deployment configuration. This is where we get into the weeds a little bit on the GPUs. What are the resources we're going to use to support this model when it's running? And you'll notice that we have these, it's kind of hard to see here, but this concept of a VM class. Actually, by raise of hands, how many of you are familiar with VM class and are leveraging that today? Okay, so a handful. You'll see this more and more. It's a concept that is built into vSphere. You can set them up in vSphere, but the idea here is it's a template for resources. So we have the VMware class in the middle identified here. We've named it A100 ADC Large, and it's going to have 16 virtual CPUs, 128 gigs of RAM, and you can see on the end it actually is backed by a full A100 GPU with 80 gigs. So keep that concept in mind because Justin's going to go over it a little bit more, but it's kind of key to how we deploy things. After identifying a VM class, we'll identify a storage class, and you'll notice on the far side, on the right-hand side there, YAML code is being built as you go through and develop this form. And that's because we're going to be deploying this on a Kubernetes node. We would hit next, it would deploy. I'm not going to, actually next is a review and deploy, I should say. We're not going to show you that, but what I do want to show you is this API gateway. When we deploy that model, as I said, it's going to be in a Kubernetes cluster behind an API gateway. And this gives us a lot of capabilities. You'll notice on the left-hand side, OpenAI API. We leverage that OpenAI spec, and that's key because if you have teams already building front ends to stuff that's reaching out into OpenAI or really any of the other major providers of models right now, they'll be able to redirect that on premises. And of course, there are a lot of benefits for that. But the other thing that's important here is that putting it behind an API gateway gives us a lot of capabilities of how we manage things. And this comes down to being able to have multiple replicas of a GPU, or correction, of a large language model, each sitting on its own GPU, on different nodes, on different hosts. This gives you not only failover capability, but scale capability. You can quickly and easily scale this up or down as required. It also means that you can very easily swap out models. If you're on Llama 3, for example, and you want to move it up to Llama 4, you can push that model out behind the API gateway and then switch it over very easily from one to the other, transparent to the users, whether they're connecting via curl, CLI, web UI, whatever the case. The other capability that we have here is it's not just a one-to-one ratio where you have one chatbot and maybe one model underneath. The idea is that you might have multiple chatbots, multiple apps, all using one model to saturate that GPU. A lot of times models only take a few number of hits per exchange. So if you think of what we're running internally, we're using a large language model for some of our code completion. Well, that becomes a pretty intermittent thing. It took us 200, we can support 200 users plus on a single model that is running on a pair of A100s. So a lot of capability when we use this API gateway here, and a lot of ability to be really efficient. So why GPUs? This is a question that comes up a lot. Hey, can't I just run this on CPU? And for small models, you can a lot of times. Small being the key word, less than 15 billion parameters is probably the safe bet. And the GPUs, or correction, the CPUs you'd want to use if you're running on CPU would be Gen 4, Gen 5, or newer on the Intel side. But GPUs themselves tend to map much, much better to this use case. They have thousands of cores instead of a CPU that has, 32, 64, 128 cores. And even though these cores aren't as fast or as complex as CPUs, the fact that you're going to have 16,000 of them on a single card allows them to handle those billions of parameters, those billions of neurons that are in the model. Many, many small, simple calculations. So that parallelism comes into play, so does the bandwidth. The bottom line is a lot more performance and actually a lot more efficiency out of GPUs. And that's why so much of a focus on them. So now let's talk about virtualizing GPUs. We're all familiar with virtualizing CPUs. We have the host, the hypervisor, and then we'll have the virtual machines with their respective apps running on top of it. Simple enough. We had a few more components when we're talking about GPUs. Within the host, we have the GPU, and then we install a vGPU manager as a VIB in the hypervisor. On top of that, we now have our virtual machines, and we can deploy the NVIDIA drivers within that guest OS to be able to use it. Now, we call them virtual GPUs a lot, or vGPUs, but it's not actually GPU virtualization in the same way that we have CPU virtualization. Justin's going to go into that in a little more detail, but one key distinction here is you can't overcommit. And a lot of people miss this. In a CPU, you can overcommit on both the compute and the memory. We don't do that with GPUs. So there are ways that we can be more efficient, but it's not the same as being able to throw a bunch of workloads on a GPU and let it handle it in a best effort sort of way. So keep that in mind. What it actually is mediated pass-through. And you'll hear that term a little bit more, but that means that after some initial connections, the exchange between the virtual and the machine and the GPU is direct. And one of the benefits of that winds up being performance. So effectively, I like to say we have bare metal or near bare metal performance. There's a couple of graphs you can see on the, bars on the right-hand side that show there's one or two situations, isolated situations, where because of our scheduler, we actually come out slightly ahead. But on average, we're usually just a little bit behind bare metal, 1% to 2%. That's a good trade-off, I think, my personal opinion. Of course, I work for VMware, but most customers feel that that's a pretty good trade-off for the agility and the increased utilization you're able to get out of these very expensive GPUs. There's actually two ways to deploy GPUs on our infrastructure. On the left-hand side, you see dynamic direct path IO, aka pass-through. And in this situation, we have a direct connection between the virtual machine and the underlying GPU. On the right-hand side, we have NVIDIA vGPU, and most of what we're talking about today will be that. It provides us some additional benefits. vMotion, Justin will talk about that a little bit more, and then the ability to slice GPUs. So where in the first case, we can have multiple GPUs or a single GPU assigned to one virtual machine, we can't do the opposite for pass-through. But for NVIDIA vGPU, we can. We can not only have multiple multiple GPUs or a single GPU assigned to a virtual machine, but we can take a GPU and we can slice it up into fractions and assign each fraction out to different virtual machines. And that gives you a lot of flexibility, especially as these GPUs get more and more powerful. A lot of memory, a lot of capability behind a single H200, or especially with the new Blackwell GPUs on the horizon. So let's talk about the fractionalization of these GPUs. Two approaches, time slice and MIG, as you saw in the previous slide. With time slice, we're doing exactly what it sounds like. We're slicing up time. We're slicing up time on those cores. So each of these virtual machines in this 4 virtual machine scenario that is leveraging this single GPU below is going to get a quarter of the time of 100% of the GPUs. So what happens is 100% of those GPUs are allocated to that first virtual machine. And then for a fraction of a second, the second virtual machine and the third virtual machine and so forth, and then back and forth. It's a round robin. So a fraction of the time for 100% of those cores. Now it's the opposite for the memory, for the frame buffer. We divide that from the beginning, 25% of the memory dedicated to each of the virtual machines. Okay, and the sharing options, there are 3 different approaches: best effort, equal share, fixed share. Best effort is what I'm talking about. That's the default. It's what's recommended. And it brings an interesting capability, and that is that, let's suppose 2 of these virtual machines were effectively sitting at idle. There was no work to be done. Well, you don't want 50% of the time just going to waste. And so with best effort, it's going to continue to give effectively 50% of the time on those cores to each of the remaining 2 virtual machines. That gives you a performance boost, which is what a lot of customers want. Now, not every customer wants that. Some customers say, hey, these 2 virtual machines were sitting at idle for weeks, and my internal customer got used to having that extra 25% on his workload. And then when those workloads came back online and he was back down to what he originally had, or she, there was frustration. Why did I see a performance drop? And so you can use equal share or fixed share to provide something a little bit more stable. All right, so that's the idea behind time slice. And that is the default. It is on every single GPU available from NVIDIA. And if you think you're going to dedicate an entire card to a workload or multiple cards, then default, you would want to use the default of time slice as well. Here's what it looks like inside a virtual machine if you're setting up the profile. The profile name will be grid, the name of the card, and then the amount of memory. So in this case, 8 gigs of memory out of 40 gigs. This is effectively 1/5 of the card. So you would expect to be running 5 VMs typically on this. So that's time slice. Well, what about MIG? How many of you have heard of MIG before? Okay, good amount. MIG stands for multi-instance GPU. In this case, instead of time slicing, we're doing spatial slicing, where there's a physical card, and that physical card has dedicated channels, 7 of them, numbered 0 through 6 there. And each of these channels has its own streaming multiprocessors, its own cache, its own frame buffer. They are effectively isolated from each other. This is really great for a multi-tenant type scenario. Or if you really want to eliminate that challenge I said a minute ago, where you have kind of a noisy neighbor situation, or what happens in one channel does not affect another channel. So for example, if I have a workload running on slice 0 there, attached to one VM, and then VMs on every other slice as well, but all of those happen to be sitting at idle, well then 6/7 of that card are going to waste. Or at least they're not being leveraged at that time. So there's a trade-off there. You trade off with a little bit better security, a little bit better isolation, or a lot better isolation, but you don't have the ability to consume the work being done by, or the cores, or the time on the cores. These slices can actually be combined in any number of ways. So you could have one slice, or all 7 slices rather at the top, dedicated to one virtual machine or one workload. Or at the bottom, you could have one slice for each of 7 virtual machines. Or you could do something like we have highlighted in green, where you have 3 slices allocated to one virtual machine, 2 to another, and yet a single to a third. And you can see all the profile names here. And if you're in the UI, you'll notice that the profile names are a little bit different here. Once again, we have the grid and the A100 to show the card that we're using. But here it's going to show how many slices are being consumed by that profile, followed by the amount of memory. So that's what those means. And if you wind up in a situation where you see in the options list, here you can see in this option list, we're only showing MIG profiles. In the case that you have a host that has at least 2 GPUs in it, and one GPU is set to time slice, and the other GPU is set to MIG, then you would actually see all profiles in that menu, and you'd be able to choose between them. Okay, so here's kind of an overview of the benefits of each, the time slice and the MIG. It's a round-robin approach on the time slice side. 100% of the cores, as I mentioned, given to one workload for a fraction of the time, and then the frame buffer divided equally, as opposed to the MIG, where we have these 7 channels that can be allocated as we see fit, providing a little bit better performance, or not performance, security and isolation. Let everyone get their pictures. Good slide. Okay, what about multiple GPUs? That situation comes up a lot, especially as we have bigger and bigger large language models that need to consume these virtual machines, or these GPUs rather. There's a couple of different ways to do this. The underlying technology is called NVIDIA NVLink. And here you can see us leveraging that with 2 cards, PCI cards tied together via these NVLink bridges, 3 different bridges connecting these. Now this is really great because it allows the 2 cards to pass information back and forth without that information having to round trip through the PCI bus and the system memory and CPU. This is just 2 cards. The newest hosts and the newest technology allow up to 4 with a single bridge going across them. So that's a pretty nice capability. But there's also the ability to do this in the motherboard. There's a technology, you'll see at the top, SXM is the format, HGX is the board. How many of you guys have heard of NVIDIA DGX boxes? Probably most people. We don't virtualize those boxes, but what we do virtualize are the HGX boxes. Effectively the same architecture, but it's going to be provided by Dell, HP, Supermicro, the usual suspects. So multiple different options when you want to have this infrastructure. And what that underlying infrastructure is what you see on the right-hand side. 8 GPUs tied to a motherboard, and on that motherboard is that NVLink in the form of a switch. And here's what it looks like, all right, so much for my clicker. There we go, all right. Here's what it looks like. So you have the NV switch connecting all of these GPUs. Well, that gives you a ton of flexibility. Now you have the ability to say, if we want to run a really large model, then we can consume all 8 GPUs just to support a single model. That might be like one of the biggest DeepSeeks, or Llama has a 405B, something like that. And all of these GPUs communicating over that NVLink switch. On the other hand, we can break this up using our device groups. Here we're showing it broken up with a pair of GPUs in one device group, another pair in another device group, and 4 in yet another, when you wanted to connect, say, 2 GPUs or 4 GPUs to a particular workload. But we can take that a step further if we want. With 8 GPUs, if we wanted to use MIG, for example, at 7 slices per GPU, that's 56 slices of GPU that can be put against 56 different virtual machines, all within a single host. So that's a pretty good amount of flexibility there. 8 GPUs to one virtual machine, or those same 8 GPUs sliced up and supporting up to 56 virtual machines. And that's the part of the power of virtualizing. It's that flexibility. Not only to allocate them in the first place, but to reallocate as things change, rather than having your GPUs confined to these bare metal clusters that are fairly static. This is where we ask our customers who are running GPUs on bare metal, what's your utilization rate? Very rarely is it above 50%. Ask yourselves, if you guys have bare metal, I see people nodding their heads right now. If you have GPUs in your environment running on bare metal, what's that utilization rate? Probably not above 50%. Okay, let's talk about monitoring and operations a little bit. We want to give you guys visibility into the GPUs so you know what's happening. So we built a couple dashboards. These first two have been around for a while. The second two are a little bit newer, but the first one thing we want to do is just give you overall visibility in the form of a heat map. We're looking at temperature and utilization for both GPU and memory, or GPU memory and GPU compute. Gray means it's sitting at idle. It used to be red. That's a whole nother story that we won't get into. Bad design decision. But anyway, gray means it's effectively sitting at idle from a utilization point of view. But this is good. This is important information to know. Who wants their GPUs sitting at idle all the time? They're super expensive. If you have a project or a team or an individual that's not leveraging the GPUs you gave them, then it might be the right time to reallocate that to a team or a project that is in desperate need of more GPU power. So this allows you to get the most use out of the GPUs that you own. Temperature is also important because GPUs can burn out. They will burn out if you run them too hot, too long. I'm seeing people nodding at that as well, maybe, and smiling. I don't know if people have experienced this firsthand. So we give you a look at, from a temperature point of view, what it looks like, but also we alert on once thresholds are met that you might want to take a look at a particular GPU. We also want to give you a view of what GPUs look like across the environment from, hey, where are they? So in the top, we see the GPU clusters. Now, we just have one cluster in this particular environment, so there's just one there, and that particular cluster is highlighted, which allows us to see what's in that cluster. So the next section down below that shows the 3 hosts that are in that cluster. And then you can see of the host, the first one is highlighted once again. And so that gives us visibility drilling down further into the GPUs on that host. So from an infrastructure point of view, a really easy way to find a cluster, the hosts, or the GPUs within there and see what's going on. Here's another similar view of what we have in the environment from the point of view of what's providing out GPU. These are the hosts that have GPU, the GPU available, several graphs around that. But probably the more compelling thing is the next dashboard we have is about consumption of GPUs. And we only have one virtual machine running in this environment. So not a lot going on, but the bottom line here is you can get a list of all of the workloads. It's not just about what GPUs are running on hosts, but we understand which VMs are leveraging the GPU they've been given, which actual workloads. So this gives you visibility into that. And you can see very quickly what's running, what's really leveraging the GPUs, and what's effectively sitting at idle. Most of the time, sitting at idle means that you'll see some amount of memory being consumed, but you won't see any compute. That means the model has been loaded into memory, but no one's doing any inferencing on that model, for example. So that's a look at our GPUs. And now I'm going to hand it over to Justin to walk us through the direct path and pass through conversation in a little bit more detail.
Thanks very much, Sean. Great presentation. Okay, this section is kind of a refinement, some aspects of 9.0 in here, VCF 9.0, and my ambition is to take over R&D completely for GPU work inside the core VCF. So you'll see a lot of new things coming up here. So everybody's used the term pass-through. As Sean explained, it's a direct connection between a VM and a GPU. We're encouraging people to use the term direct path because up to now we've made a big distinction between pass-through and virtual GPU, but they're actually variants on the same spectrum. They're very, very close to each other, in fact, and that's what this section is going to be about, very brief section here. So just above the GPUs there, above the machines, you see direct path. That's the foundation for everything. It's the foundation for pass-through. It's also the foundation for vGPU. So as Sean said, once you've passed through that guest OS driver and the host driver in the vGPU case, you're operating in direct path mode. You're operating as if you were in pass-through. Those drivers are simply gateways to stop you from accessing more of the GPU than you're entitled to. But from that point on, you're in direct path mode. And that's the reason that vGPU performs so well, because most of the traffic is going directly to the GPU. And so there are at least three forms of this. The fixed direct path I/O on the left-hand side is what we all know as pass-through. Let's use the term direct path for that because that's probably a more applicable term. The vGPU method is mediated pass-through. There's a driver in the way. That host driver is in the way, and it's preventing you from using more of the GPU than you're entitled to. And you're entitled to use what your virtual GPU profile allows you to do. So you saw Sean use a 20C or an 8C profile. That means you're limited on the space you can use on that GPU. Enhanced direct path I/O, you might have heard of, this was Project DVX inside our core GPU people. And this is doing virtualization in the same way that vGPU does, but for network cards and for other vendors' GPUs. In the future, when these drivers get written by other vendors, we will have the equivalent of vGPU for those others as well. So that's a quick background on terminology there. A new thing that came out with 9.0 was one of our core things, vMotion. Who here has done a vMotion on a VM with a GPU attached to it? Tony's definitely done. Maybe a dozen people have done. You can vMotion these vGPU-aware VMs just like you did with regular VMs. It's just that the target must have the appropriate GPU ready to receive it, the target host. So the vMotion team in Palo Alto took this idea and said, we're really going to improve this in a big way for GPUs. And this is the way they improved it. Between the left-hand vertical bar there, far left, and the vertical bar that says stun, a lot of data is being copied from the source machine of a vMotion to the target machine of a vMotion. All of the memory that we've described in the VM itself, the CPU memory, and all of the memory that makes up an 80 gigabyte GPU must now be copied from source to destination. And in previous versions of VCF or vSphere, all of that copying was done during stun time. But it turns out that large language models help us here because something like 70% of the data in the GPU, when a large language model is running there, like Llama 3 or Llama 4, 70% of the data is fixed. It's the weights in the model which don't change at inference time. So 70% of the data could be copied during the VM being alive and running, while the VM is not stunned. And the engineers spotted this convenient thing and said, let's do a pre-copy. Before we stun the VM, 70% of the data can be copied because it's not changing, and then only stun the VM for that 30% of the data which is dynamic. It's in technical terms, this is the KV cache, the key value cache in a large language model. It's the only dynamic part of that model. So vMotion is making use now of features that we get from Intel and from AMD CPUs and identifying that data that is not changing and pre-copying that data before we stun the VM. So, okay, very technical point here, but what's the benefit of that? The important column here is the comparison against VCF 9.0 stun time, 5 columns from the left there. What's running here is a single VM running a model, Llama 3.1, 8 billion parameters is a small version, and 70 billion parameters is a medium to large version of that model. There are different versions of these models. So this is a single VM running on L40S and on H100 GPUs in the second column here. And you can see in the comparison, we take 3 times less time now in stunning the VM than we did at 8.x. 3 times less time in stun means your application is stopped for 1/3 the time that it used to be. And the astonishing number on this picture is the last row. That's a 70 billion model running on an 8 H100 HGX card that Sean showed you a picture of just now. So this is 8 GPUs, each with 80 gigs, 8864, that's right, 80 gigs of memory on it. So that's 640 gigs of total physical memory, of which 90% is used by the model, 576 gigabytes, half a terabyte of data is being vMotioned from one machine to another. Now, a few caveats here. They used a 100 gigabit network for the vMotion. And the reason we can do vMotion is this model is running on top of a platform called vLLM. vLLM is a runtime model for models that is very contemporary, came out of UC Berkeley, and it doesn't require a feature that NVIDIA's runtime requires, which is UVM. It doesn't require unified virtual memory. So those are the two caveats. But 21 seconds of stun time for half a terabyte of data is pretty amazing. It means the application will not notice this vMotion happening. The actual LLM that's running here may not notice that the VM has been stunned. So you take all of that HGX card, that high-end card that Sean showed you with 8 GPUs in it, and you vMotion a VM that's using all of it to another machine. That's pretty serious investment from the vMotion team. Okay, that comes in 9.0. You heard Sean mention VM class. The way I think about VM class in the GPU world is a wrapper around a vGPU profile. And VM class was introduced when we introduced the supervisor. It's the idea of being able to apply vGPU profiles to Kubernetes clusters. That's what VM class allows us to do. So these are built-in VM classes. You can see their sizes of different shapes and sizes of VMs, just like templates, but here they're VM classes. And we create these in the VM service. So we go to VM service and create one. I'm going to create one now in a second. These are all created by the end user to represent different shapes and sizes of GPU allocation. So in the case of my lab, I've got 40 gigabytes of memory, so I would use the 40C GPU there as the VM class that I would assign. And we're spending a lot of time on VM class because it's going to be used by more sophisticated features above it that you'll see here in a second. It's a building block for bigger features like being able to reserve a GPU in advance, that type of thing. So these VM classes were created by an administrator. They're pretty informative about what they mean. They mention the amount of memory that they refer to. That's a best practice. You could name these Joe and Sally if you wanted to, but that wouldn't tell you anything about what they're doing. So these have been very carefully named to indicate what type of GPU they refer to and what amount of memory they refer to. And so we're going to create a VM class here. We choose a name, A100 HC GPU here, and we decide what version we're using. And the big decision we need to make here is how much memory do we give it? By the way, watch this part carefully because it presents to you in megabytes. What you really want is gigabytes. All right, be careful with that one. And then we add a PCIe device to it. How many people here have added a PCIe device to a VM in the past? And how many of those PCIe devices were GPUs? Most of you have done it. Great, great. So this is very familiar. Now, if you were listening carefully during Sean's part of the presentation, what kind of profile is this 1C that is at the bottom here, or this A100-1-5C? Hands up for MIG. Hands up for time sliced. It's MIG. Well done. Well done. So that's a MIG one, and this is a time-sliced equivalent profile. So by virtue of having that extra number in the profile, you can tell whether it's MIG or time-sliced. The extra number gives you the number of cores, or sets of cores. So we're allocating a GPU profile. We do that. We go down and go through the other steps and say finish, and we've got our new A105C GPU on the bottom there, a new class. So now we can construct Kubernetes clusters with that class to create VMs that will store that amount of GPU power. Okay, we're going to get a payoff from this VM class in a minute, but we need to do one more thing before we do that. And this is a brand new concept in 9.0 called Direct Path Profiles, DPP. I always found the term DPP kind of scary, the Director of Public Prosecutions, but it's Direct Path Profiles here. Direct Path Profiles, and you're seeing me use the word direct path instead of pass-through here. So this is with reference to vGPU now. Direct path profiles are another wrapper around the vGPU profile. We're going to use the vGPU profile to create one, and they will allow me to see much better GPU visibility inside vCenter, consumption inside vCenter. So you saw it inside VCF operations, but now vCenter is going to give us some visibility as well. And so we're going to create one of these by selecting the vCenter. We're in a workload domain here. And we choose, again, a vGPU profile. This one happens to be 40C. And we assign it a name and a description. In the description, the best practice is mention the vGPU profile name that you used. Always give it the full vGPU profile. You don't have to do that, but if you do so, you will get a payoff that I'm going to show you in a second. So we've got our new direct path profile. So now we've got a VM class for Kubernetes, and we've got a direct path profile that are directly parallel to each other. And we're going to get the benefit of that here in visibility. So this tells us, for any direct path profile that we created and its associated vGPU profile, how much is in use. So the little orange bar at the bottom says, my one VM consumed one of those profiles. The rest of it is in gray because I actually reserved all the GPUs in advance here. Meaning they're only allowed to be used by certain people inside a certain namespace. And now I'm going to show you what that means. So here's a setup where I have two hosts, or perhaps two GPUs on the same host, and I have two VMs. And those VMs have consumed a 40C profile each. And by default, vSphere's DRS scheduler will place these VMs onto separate GPUs. It won't consolidate them. You can tell it to consolidate them onto the same GPU, but it doesn't do that by default. And so those two GPUs now are half occupied each. And on top, I've got an 80 gigabyte requirement. I've got a VM that wants 80 gigabytes, and there is 80 gigabytes available. It's just not available on one GPU here. And so with reservations, and this is something particularly applicable to cloud providers, with the new feature of reservations, which makes use of VM class and makes use of direct path profiles as its underlying technology, I can now reserve that right-hand GPU and say, nobody touches the GPU until Justin, with his privileged namespace, decides to fire up a VM. It's completely reserved for me from day one. And this is to allow a cloud provider to say, Mr. Customer, I promise you this A140 gigabyte GPU, and nobody else, no other consumer, no other tenant will get it until you arrive. So it's pre-allocation, pre-reservation. This is brand new in 9.0 as well. So thank you very much. Please take our survey. And please come to us on the booth downstairs and see Private AI in action. I'll be there, Sean will be there. So we have 5 minutes for questions. I know you're all rushing off for coffee, but those hardcore GPU people, fire questions, please. If you do, please come to the microphone so we can hear your question. Yes.
Is there a specific reason why you only support HGX and not DGX?
Say again, please.
Is there a reason why we support HGX but not DGX? Is that the question? So there's a couple reasons behind it. The technical reason moving forward right now is it's running on ARM, and obviously what we're virtualizing in production right now is on Intel based. And I think that was the basic idea behind it. There's no other reason we couldn't virtualize DGX boxes. We've virtualized the Intel versions of them in the past. It was just at a point we were working with NVIDIA to determine whether or not we should do this. And because of that switch in ARM at the moment, it was determined right then that we shouldn't. So that's where we are today.
Do you see requests coming from customers?
Microphone, please.
Do you see requests coming from customers doing virtualization on DGX?
We do have that question all the time. In fact, a lot of customers come to us assuming that we can virtualize DGX and then disappointed when they find out we can't. So, and if you're one of those customers and you want that, please reach out, send us emails, your company name, and that you want that, and we'll add that to the list to inform our leadership as well as NVIDIA's leadership that it's worth the effort to do that.
Two questions. When are you guys going to start supporting AMD?
That's a really great question.
So
Go ahead.
So there is ongoing work with AMD to support their GPUs, and the MI350 should be in the works. I won't say exactly when.
And the second question, the support for custom runtimes. Our development team has specific requirements, and we would like to use a slim version of the runtime. Do we have the capability to create our own and plug it in directly into the NVIDIA platform?
Into the private AI services platform? It does give you an option to use one of a set of runtimes. So VLLM I mentioned, Triton inference servers, another. If you come to us
I don't
with
think we have Triton right now. I think we have Infinity.
yeah, Infinity.
But there are more on the horizon. But your question is about a custom one. It sounds like you have your own runtime.
We have our own, yes. Can we bring that in?
As of today, you can't bring that in. You cannot bring that in. Okay. But let me push that out to the team to try and gain that support. And please reach out to us.
It would be a request to a product manager,
Actually,
yes.
Can you go to the next slide so people can see our contact?
Okay.
Reach out to us and send these requests, because we'll work directly with the product team and say, hey, these customers want this. That's how we gain momentum to prioritize what comes next in the solution.
You guys can see what we have ready together. You can see actually.
Yeah.
That'd be great.
That even get to the next level, right?
Okay.
Good.
See you guys later.
Are the slides available anywhere that you just presented?
They will be. The session itself and the slides that accompany that will be made available. Usually takes a week or two, but in the coming weeks for sure.
What are some of those thresholds that you guys alert on? And are there any other metrics that are worth monitoring?
Yeah. There are metrics that you can get through a subsystem called DCGM, data center. So you're using that already. You're probably using it with Prometheus and Grafana to analyze that data. Metrics like KV cache size and growth would be important in the large language model area.
Okay.
Yeah.
Quick question. So we're using pass-through now. We're in the process of converting over to using vGPU. And for the profiles, right now we only have one application that's utilizing the GPUs, but we want to build it so that if other applications come in, that they can leverage it as well. So when we're thinking about applying those VM profiles, do we need to, like, if we were going with the MIG method, do we need to leave space or leave channels available for like that vMotion when, you know, certain apps are being migrated to other hosts? Or if we fully commit that, do we run into a situation where we can't migrate those VMs without some type of interruption?
This is an interesting question because there's a couple of different components to it. So first, for the vMotion, you're going to want to have the equivalent resources on a second host. So if you have an A100 GPU, then you want to have the same A100 GPU on an equivalent host so you can migrate to it. And as of right now, if that target card is full, then that vMotion will not happen. So you would need, in that case, to have slices maybe available on each so that you could go in either direction if that's the approach. Now, we are looking forward to ways to preempt in the case that you might have some workloads running on that second one, but maybe they're not quite as important as a production workload that just went down and you want to restart somewhere else. But as of today, you would need to have that space allocated.
Thank you.
On the slide about the SXM form factor, you gave an example of the 8 GPUs, and you can obviously carve that up and assign 2 GPUs to one VM, 4 to another, etc.
Exactly.
If you've got two GPUs with NVLink, obviously you could present that using a device group, so you get the pair to a single VM. Are you bound to always having to do that, or could you actually assign a single GPU to one VM, a single GPU to another, or use vGPU? Once you've got that physical bond between them, are you forced to do that as a pair?
You can certainly avoid using the pair. You can say VM1 gets GPU1, VM2 gets GPU2, but what the GPU driver does there is switch off the NVLink.
Perfect. That's the answer that is incredibly hard to find out. Yeah, thank you.
Thank you.
Currently with vSphere 8, there's a limitation that doesn't allow me to apply pass-through CPU virtualization to a VM that already has pass-through to a GPU. Is there plans to change that, or will the vGPU option?
The second pass-through was?
For CPU virtualization, so like VTX, for example. Yes.
They're mutually exclusive, right?
Correct. So, for example, I have a VM that's running Windows operating system. The user needs access to the GPU, but they also need WSL. And WSL requires CPU virtualization pass-through. And so because they're mutually exclusive, I can't provide that as a VM. I have to provide it as bare metal.
Yeah.
So is there plans to support that in VCF9 or in the future?
Nested is tricky for us because the driver needs direct access to the physical GPU, and it's not getting it in a WSL situation. So we'll take that question back and try to get you an answer if you leave your contact with us.
This goes back to the original statement I made about we call it vGPU, but it's not true virtualization. That abstraction layer is not the same. It's actually mediated pass-through. So that, is part of where that problem comes about. But reach out to us and ask that question, and we'll make sure that the right people prioritize that accordingly.
If you pass through once to the Windows operating system, then passing through again from Windows to WSL is a double pass-through that, as you said, is not supported today. But there may be something in R&D that we can find out for you.
I was wondering if direct path might be something that addressed that.
It's for one layer of pass-through only today.
Okay, great. Thank you.
Welcome.
Thank you, everybody, for joining.
Thank you.